Hello, this is Dr. Lennon, and we're going to talk about antiderivatives. So, what is an antiderivative? Essentially, it's just the process of the derivative in reverse. So, if we write down the definition, it would say a function, capital F of x, is an antiderivative of another function, little f of x, on an interval I. So we'll say I in case the function doesn't have a domain of all real numbers, or we're just talking about a specific section, any number of things. But provided when you take the derivative of capital F of x, you actually get little f of x. So you might recall that in general, antiderivatives are pretty much the same, but there's infinitely many of them for any given function, but they only differ by a constant. So we could say if capital F of x is an antiderivative of f of x, then we could get all the possible antiderivatives by looking at f of x plus c. So this is known as the family of antiderivatives. Where c is an arbitrary constant. So we'll see later that when we're finding indefinite integrals, we'll want to include that c, but when we're computing numerical values of definite integrals, it's not so important. So let's just do a couple basic examples with maybe some polynomial or power functions. So let's say find the antiderivative, or let's say find the family of antiderivative of each function Okay, so what functions? Let's start with part A. We'll say f of x is 1 divided by 2 square root of x. So whenever you're finding antiderivatives, or derivatives also, for that matter, if you recall from Calculus 1, usually if you have a function of x, and you can rewrite it as an exponent, you want to do that. So we could rewrite this as 1/2 times x to the negative 1/2 power. Right, because the square root is the 1/2 power, and to be in the denominator is the equivalent of having a negative exponent. So we know that derivatives decrease the value of the exponent by 1 when we have a power function. So antiderivatives are going to do the opposite. They're going to basically increase the power by 1. So we might say, okay, capital F of x, this could be equal to x to the 1/2, so we could kind of check and say, okay, well, if we took the derivative of that, we would have 1/2 x to the minus 1/2, so we just want to stick a, so that looks like that'll do the job. And then if we want the family of antiderivatives, we just add a plus c to the end. So that would be the case there. How about another example? Let's look at B, maybe just an ordinary monomial. So B, let's suppose we have g of x equals 4x cubed. Again, this one is fairly straightforward because capital G of x, we know that differentiation would decrease the power by 1, so our first guess might be x to the 4th, and we see if we took the derivative, that 4 would come down in front and we'd get exactly g of x. So then to get the family, we would just add that plus a constant. Okay, so maybe one last simple one. Let's say we have h of x is equal to 17. Okay, well, what would have a derivative that's actually equal to a constant? Well, that would just be a number multiplied with x. So our antiderivative here, capital H of x, would be just 17x, and then we would add a constant to it. Remember, this is basically just a linear function, and the derivative of a linear function would just be its slope. So this antiderivative process is really just going backwards. So it's not so difficult to guess the formula for power and polynomial functions. So that's known as the power rule that allows us to find the antiderivatives here. So let's say antiderivative, because we do have a power rule for derivatives also. So the antiderivative power rule is what? Essentially, if you have a, you're trying to find, so let's say given f of x is equal to some function that looks like x to the n, we would want to find what is the general antiderivative of that expression x to the n look like. So the general antiderivative is capital F of x is equal to x to the n plus 1. The power has to be 1 bigger, and then to account for that coefficient, we would also want to divide by n plus 1, and then we have our general constant. So that is the antiderivative power rule. So let's just add some notation in here. So notation, usually we're not going to write out a whole sentence saying this is the antiderivative and so and so. So what we have is what's known as the integral, and the indefinite integral is this elongated s. So if we would write the expression where we have this integral symbol, we have our integrand, which is the formula that we're trying to find the antiderivative of, and then we have the differential at the end, dx, which is one way to, so that's the limit of the partition of the Riemann sums when you're constructing the integral. But you could kind of just look at it and say, okay, that's where the integral stops, and it lets me know what the variable is that I'm interested in integrating. So this is x to the n plus 1 over n plus 1 plus c. So let's just note that the integral of f of x dx is called the indefinite integral. It would be a definite integral if there were limits at the top and the bottom of the integral symbol, say going from 0 to 5 or something like that. And then it would have a numerical value. So we'll look at definite integrals in the near future. So this is called the indefinite integral of f with respect to x. To evaluate, we just find the family of antiderivatives of f of x. So in the short term, all the shortcuts that we had derivative formulas for, we will have antiderivative formulas for. And then for all the techniques of differentiation, product, quotient, and chain rule, we'll develop some techniques for antiderivatives to figure out what those are. But it's important to realize that not every function can be integrated with respect to elementary functions. There are many functions where that can't happen. E to the negative x squared, for instance, or sine of x over x. Those don't have elementary antiderivatives. But for the most part, we can integrate lots of things. So this notation you can think about right now is just kind of a shorthand for saying if they ask you to compute an indefinite integral, you're just finding the antiderivative. That's really all that we're doing right now. Okay, so what about some other properties? So we saw that the derivative behaved nicely with respect to linearity, meaning you could bring a constant out of a derivative, or you could add two derivatives by doing the derivative separately and then adding afterwards. Well, it behaves just as nicely, both of those properties, with respect to the integral. So let's say sum and constant properties. So let's say suppose f is integrable, meaning it has an antiderivative, and so let's suppose f of x is integrable. F and g, I need two functions here, I'm sorry. F and g are integrable, and we'll say k is a constant. Then we have two kind of properties. We can say that the integral of k times f of x excuse me, k times f of x is the same as k times the integral of f of x dx, and also two, if we have the integral of f of x plus g of x, this is the same as the integral of f of x dx plus the integral of g of x dx. Okay, so actually, I'll leave it to you. From both of those two properties, you can verify that it also works with difference. F of x minus g of x would be the integral of f minus the integral of g. Basically, just apply properties 1 and 2, allowing k to be -1. So just for a quick example, let's say compute, let's say the integral of 5x minus 1 times 2x plus 3 dx. Okay, so now these things are multiplied together. So again, this property doesn't work with factors, it only works with respect to summands. So we have to perform some algebra. So the first step would be, okay, multiply this thing out. We will learn about integration by parts, that we can do this with products, but we don't have that yet. So we are just going to multiply everything out and then go term by term using the two aforementioned rules. So basically, we can start by saying that this integral 5x minus 1 times 2x plus 3 is the same as the integral of 10x squared. Then we have plus 15x minus 2x, so plus 13x minus 3 dx. And then we just go term by term. So for each one, we're just using the power rule. So we'd have 10x cubed over 3 plus 13x squared over 2 minus 3x plus our constant for the family of antiderivatives. And there you have it. So from there, you can see that you can find the antiderivative of any polynomial pretty easily. Okay, so let's think about trig functions. What are the antiderivatives of the trig functions that will be easily available to us right now? So let's recall the derivative formulas for the trig functions. So we have 6 trig functions that we want to know the derivative, or that we theoretically have computed the derivative formulas for, and I think they're worth memorizing. Of course, sine, cosine, and tangent go without saying, but even cosecant, secant, cosecant, and cotangent, it's good to memorize those because it takes a bit of time to go ahead and apply the product and quotient rule for derivatives. So anyway, let's think about the derivative rules. The derivative of the sine of x we know is the cosine of x. The derivative of the cosine of x was negative sine of x. The derivative of the tangent of x, if you recall, is secant squared of x. So those are the three main ones. And then let's see if we can remember the derivative formulas for the reciprocal trig functions. So for 5 and 6, let's say the derivative, we want to do the derivative of secant of x, cosecant of x, and the cotangent of x. And again, if you want to work these out for yourself, you can go back and just change, say, secant into 1 over cosine and then apply the quotient rule to get that derivative. So the derivative of secant x is secant x times tangent x. The derivative of cosecant x is going to be negative cosecant x times cotangent x. And the derivative of cotangent is negative cosecant squared of x. So for each one of these, we can associate an antiderivative formula. So basically, if you take the result and do the integral of that, you will get the thing that you were taking the derivative of. So let's see how we can rewrite that to get some antiderivative formulas. Basically, if we took the integral of the cosine of x, well, we now know that that is going to be the sine of x plus a constant. If we took the integral, so you could put the negative on either side, but generally the way you do it is if you take the integral of the sine of x, the integrand, you want to keep the negative out of there. We could say this is the negative cosine of x plus c, because if you take the derivative of cosine, you would get another negative popping out, and then the two negatives would end up being positive x. So as it is right now, we don't have any kind of antiderivative formula for tangent. We're going to have to use one of our techniques to determine that later, but we do know an antiderivative formula for secant squared. So if we take the antiderivative of secant squared x dx, this would be the tangent of x plus a constant. If we would have the antiderivative of secant x times tangent of x, that would be the secant of x plus a constant. I forgot my dx there. Let me see if I can fit that in somehow. So dx. Okay, if we do the antiderivative of cosecant cotangent, we would say this is negative cosecant of x plus a constant. And lastly, if we did the antiderivative of the cosecant squared of x, this would be negative cotangent of x plus c. So going backwards with all of our derivative formulas, we have now found 6 antiderivative formulas that we can apply here. So let's go ahead and look at an example where we apply some of these. Okay, so let's look at 2 examples here. So let's just say compute. We're just finding antiderivatives. So the first example, A, let's compute the antiderivative of 2 over pi times the sine of x minus 2 cosecant squared x dx. A lot of places require that you put like parentheses or on whatever you're integrating around it. I generally don't, so a lot of times I won't include these parentheses here. I think of them as kind of superfluous, but if you're graphing on like Desmos or something like that, I think they do require that you put the parentheses there. I kind of just understand that between the integral and the differential, that's going to be the integrand. Anyhow, so the first thing we want to do for this one is we just want to kind of break up the integral. So you can break it up using the sum and difference formulas that we talked about. So we can write this as 2 over pi integral of sine of x dx minus 2 integral cosecant squared x dx. And now we can apply the integral formulas separately. So we know the antiderivative of sine is negative cosine, so this is just going to become negative 2 over pi cosine of x. And then the antiderivative of the cosecant squared x is negative cotangent of x. So this is going to become a plus 2 cotangent of x, and then we have plus our general constant there. And that is all we actually have to do. So that's all we did was use the linearity of the integral, and then we used the formula for the antiderivative of sine of x, and then we used the formula for the antiderivative of cosine squared x. So they just pop out naturally there. Another example that we can look at may require that we perform a little bit of algebra to see the appropriate formulas in order to use those trig formulas that we found. So what do I mean? Let's look at this example. So the antiderivative of 4 cosine x plus sine squared of x with everybody being divided by sine squared of x dx. Okay, again, we can't break this up based on numerator and denominator because that is a quotient, and for now the integral is only behaving with sums, differences, and multiplication by a constant. So let's kind of work on that expression over here. So let's simplify 4 cosine of x plus sine squared of x before we get to doing anything else. So let's split that up over the common denominator to start. So we can rewrite this as 4 cosine of x over sine squared of x, and then plus sine squared of x over sine squared of x. And now we know that we can think of the first expression. So if you're good at trig identities, this is where that's helpful. If not, you can actually look on my YouTube page. I have another video that goes over trig functions if you want some review there. Trig identities, I mean. So let's think about the first one. We can think of this as 4 times 1 over the sine of x times the cosine of x over the sine of x. And then the sine squared of x over sine squared of x is just 1. So actually this can be simplified to 4 cosecant of x times the cotangent of x plus 1. So really this is what we want to focus on integrating, and that's going to be much easier because we have a formula for the antiderivative of cosecant of x cotangent of x. So let's go ahead and write that integral. So let me... What were we initially trying to integrate? So the integral of 4 cosine of x plus sine squared of x over sine squared of x is the same as the integral of 4 cosecant of x cotangent of x plus 1. And we can split that up again using the linearity of the integral. In general, you may skip that step in the future, or I may, because it's kind of obvious that you're just breaking it into the subsequent pieces. But the antiderivative of cosecant cotangent we know is the negative cosecant, so the first integral is just going to be minus 4 cosecant of x and then the antiderivative of 1 is just x, and then we have our general plus c at the end. So some trigonometric manipulation allows us to utilize those formulas above. So a lot of times that's why people think of these trig problems as more difficult. As I always like to say, kind of the hardest part of calculus is algebra, so that's kind of what's going on here. Again, that's why a lot of people find trigonometric identities so difficult. Really, it's just the algebra behind it. Okay, so I do want to make a comment. So the way this textbook that we're going through is ordered, they kind of exclude the exponential and logarithmic functions, but if you've had exposure to them, let's talk about those antiderivative formulas just now. So exponential and logarithmic functions. So we'll probably have to come back to this later, but for the time being, let's include those formulas. So we can kind of go the same way. We're just reversing the process. So if we think about the derivative of the exponential function, kind of there's two derivative formulas for exponential functions. You have the derivative formula for standard form, say b to the x, that has derivative natural log of b times b to the x. So reversing the process, since differentiation yields a multiplicative factor of natural log of b, integration is going to instead divide by the natural log of b. So our integral formula would look like the indefinite integral of b to the x dx would be b to the x divided by the natural log of b plus a constant. And if we were looking at e to a constant times x, this would be k e to the kx when we differentiate. So if we integrate the antiderivative of e to the kx dx, again here, instead of multiplying by k, we'll divide by k. So this will be e to the kx over k plus a constant. And then for the logarithm, the derivative of the natural log of x we have found is just 1 over x. So here, this is one little bit that is a little bit different. If we integrate 1 over x dx, we would suspect maybe it's the natural log of x, because again, we're just kind of reversing the process. But notice that if you're starting with a natural log of x, you have a domain where x has to be greater than 0. So that's going to apply to your 1 over x. So there's no problems really there, because you can't plug in 0 into the natural log of x. You also can't plug 0 into 1 over x, but negative values aren't creating any problem for 1 over x. However, if you start with 1 over x, that has domain all real numbers except for 0. So if you try to plug some negative value, though, into the result, which is the natural log, you're going to end up with something that's undefined. So that's one of the reasons we would think of this as, this is written as the natural log of the absolute value of x plus c. Again, if you know that your inputs are always going to be positive, you don't have to worry about including that absolute value there. But otherwise, you do want to include it so that you don't have some domain errors when performing the integration of 1 over x. Anyhow, I'm not going to do too much with those right now because they don't come up in the homework yet, but these are the 3 pertinent antiderivative formulas that apply to the exponential and logarithmic functions as well. So if you were curious about those, there they are. Anyway, that's it for our basic antiderivatives. So probably you've seen those before, but if not, it's a nice review. So this is Dr. Lennon signing off.